And that just having that feature creates all sorts of technical challenges in the type theory of modules. The other thing that's interesting about ML modules specifically is that they are like, if you look at the early work on ML modules, it was trying to understand this idea of building a sort of lambda calculus over these type and term containing modules in terms of dependent types, because it comes up very naturally that you want to be able to, if you have, for example, an argument to a functor, which is just a function at the level of modules that has type and term components, then you can, if you have an argument x and has a type component t, you can project out this type component t, you go x dot t. And now this looks a lot like dependent types. Like you have a type that's dependent on some, module x, which has dynamic components as well. And the thing with the ML module system is it was always really designed so that you didn't really need dependent types under the hood. Like the goal was not to actually move to full-blown dependent type theory. It was to provide something that had some of the sort of semblance of dependent types, but with a more sort of in the context of a more practical programming. And so making that work also was technically. So I mean, in some sense, ML modules came out of this early work, right? There were various dialects of ML that were developed, and so this was a very natural way of structuring large programs in an interesting way. But like a lot of the design of ML modules came from that very early work. Like you see it in the very early designs of standard ML, for example. The definition of standard ML has ML modules sort of not quite fully formed, but it was there very early on. But